In this lecture, we will study the relativity of electric and magnetic fields. Now, let us assume a scenario that there is a current carrying conductor. Let us say this is the conductor, which is at rest in a frame S. So, in frame S, this conductor is at rest and it is carrying a current I in this direction. So the negative charge density, they should be moving in this direction, and the positive charge density should be, let us say, ions. They are stationary in frame S. So the velocity, average drift velocity of positive charge is 0 in this frame, and the average drift velocity of negative charges is, let us say, V. Now let us say that there is a charge Q, which is actually negative in nature, is moving at a speed v or v naught in this direction. So since in our this frame this charge is moving, so it should experience a magnetic force, and in our stationary frame the conductor is neutral, so it should not exert any electric force on this charge. So only the magnetic force should be there in our frame S, and because of this magnetic force, this charge should move towards the conductor, that is it should feel attracted towards the conductor. Now, assume a scenario that we are looking at the situation from a frame in which the charge is at rest. So now let us say this frame is S dash. So in this frame, the charge Q is at rest. So its velocity is 0, and the negative charge density, let us say, is now rho dash minus, and positive charge density is, let us say, rho dash plus. They will be moving at some velocity. V plus should be equal to minus of V, and V minus should be equal to V. So in this scenario, uh, what we are doing, we are thinking that we are moving with these charges, the negative charges of the wire. So we are also assuming that this V naught for our special case is equal to V. So for our special case, this charge will be at now, what we say, that will be stationary. So since this charge is stationary now, then it should not feel any magnetic force. But still, we should see that it should be moving towards the wire. So, what is that force which is now pulling this charge towards the wire? So, we need to explain this scenario. So, current will be, let us say, I dash in this frame, and in this frame is we actually moving. This wire is moving with V. Okay, so we need to explain this. So, in the rest frame where the wire is at rest, in this frame the charge is going to have a force q v naught cross b, and we know that b is equal to simply mu naught upon 2 pi r I a phi. So f is equal to mu naught upon 4 pi into 2I by r into q v naught. So this is the force which we should see in frame S on the wire, which is on the charge, which is going to pull the charge towards wire. This is we have derived in one of our previous lecture, that is field due to a long wire carrying current. We can easily find through Ampere's circular law also. Now I can write this I simply as rho minus V into A, that is JA. So the force will be in terms of Q and V mu naught upon 4 pi Q rho minus A. Now we are assuming that V naught is equal to V. So it will be V square. Now I will write this this mu naught. Now you know that C square is simply 1 over mu naught epsilon naught. So I will put the value of mu naught equal to 1 by epsilon naught C square. So F will be 1 upon 2 pi epsilon naught rho minus A V square by C square. Now you should see that why I have replaced mu naught by this quantity, because this is a very famous term V square by C square, and we will see it many times whenever we study relativity. So in this way we have found the force on the charge in frame S given as rho minus A, of course we forgot Q here, Q V square by C square over 2 pi epsilon naught. So we should keep this handy at one place. Now we need to study the scenario from S dash frame. Now you might have heard somewhere that in relativity there is length contraction and time dilation. So what does it mean? It means that whenever we are observing things in a frame which is moving, then the length along the direction of the velocity or the moving direction, it contracts, and its value is given by the rest frame length into 1 minus v square over c square. But the length which is perpendicular to this motion does not change. So the volume given by v is equal to al should change in the moving frame, because this should not change because it is in the transverse direction to the motion, but this will change because of the motion. So the volume changes, but the total charge, it is an invariant quantity. That is, no matter from which reference frame we are looking at, the total charge should not change, because it is a scalar quantity and it is an invariant quantity. If there have been some case that total charge changes with velocity, then we could have easily found out through some experiments, like by heating a normal block carrying some charge, we could have increased the vibrations and velocity of the electrons or the charges in it, and because of that it should have become charged. But no physical practical experiments of heating any block making it charge are available. So it means that the total charge is invariant. So the total charge should be same in both frame S as well as S dash. That is, rho into al should be equal to rho naught into a l naught. This is the rest frame and this is the moving frame. So rho l should be equal to rho naught l naught, or it implies rho should be equal to rho naught l naught over l, or rho should be equal to rho naught 1 minus v square by c square. So you see that in a moving frame, the charge density changes. Okay, so you see that in our moving frame, let us again draw the figure in the next slide. So in our moving frame, the scenario is like this. That is, this conductor is appearing to be moving in this direction v, and charge is stationary, and the positive charge density is there now, and it is moving with some velocity given as minus v, and the negative charge density is there and it is not moving, it is stationary. So this is the scenario. So in this moving charge frame or the moving frame, the positive charge density should be now given as the rest frame positive charge density divided by 1 minus v square over c square. However, in this frame, the negative charge is not moving. So you see, in our normal frame where the wire is stationary, the negative charge was moving. So the negative charge density in the rest frame in frame S should be equal to the charge density in the frame where it is stationary divided by 1 minus v square over c square, or it implies rho minus dash is equal to rho minus 1 minus v square by c square. So we have found the value of the positive charge density and the negative charge density in this moving frame. Now you see, in this moving frame there will be a magnetic field which will be created by this positive charge motion, but this charge will not feel any force because it is not moving in this frame, so it is not going to feel any magnetic force. Only electric force should come into the picture, even though there is a magnetic field which is existing in S dash frame also because of this positive charge motion which is creating a current, but this magnetic field is not going to create any force on this charge because it is stationary. So this gives answer to first part, that there will be a magnetic field in both cases, but there will not be any magnetic force in this scenario, and there will not be any electric field force in this scenario. Now we need to find the electric force on the charge in S dash frame. Now, as I've told that in S frame, the conductor is neutral. So it implies rho plus rho minus should be equal to 0. Now we need to find the total charge density in the moving frame. Total charge density in the moving frame will be rho plus dash plus rho minus dash. So from these two equation and this equation, I can find the charge density in the moving frame equal to rho plus dash plus rho minus dash equal to rho plus v square by c square 1 minus v square by c square. So you see that in the moving frame there is a resultant charge density available on the conductor, which is now going to create a electric force. Now what will be the value of this force? So this is a conductor which is having a surface charge density rho dash is equal to rho plus v square by c square 1 minus v square by c square. So it will create an electric field which is given by rho dash a over 2 pi epsilon naught r at a point r from the axis. Let us say here the charge is present. Okay, so the force on the charge will be in S dash frame will be q into e dash. So it will be equal to q into a rho plus v square by c square over 2 pi epsilon naught r 1 minus v square by c square. So this is the electric force which will be felt by the charge in the moving frame. So let us compare this quantity with the previous quantity which we have calculated through rest frame. So in the rest frame the force is F is equal to q a rho rho minus and rho plus are equal in magnitude, v square by c square over 2 pi epsilon naught r. So this was the force which we calculated through magnetic field in the rest frame, and this is the electric force in the moving frame. So by comparing these two, we see that f dash is equal to f over 1 minus v square by c square under root. Now, from the theory of relativity, we know that force in a moving frame is equal to force in a rest frame divided by 1 minus v square by c square. So, you see that both of these forces are actually matching. That is, the magnetic force in rest frame is equal to electric force in moving frame. And in our special case, the speed of moving frame is equal to the speed of that charge, and also the drift velocity of the charge carrier in the current carrying conductor. So in this way we have shown that the electric and magnetic field which we have derived using Maxwell's equation follow the special relativity theory. And of course the reality is that the special theory of relativity was kind of motivated or had idea from the Maxwell's theory only, and the Maxwell's equation were already accurate by this factor, so they did not need to change after this special theory of relativity was uh, given by Einstein. So in this way we have shown how the electric and magnetic field depend on the reference frame. So as I have told in one of the lectures that the Lorentz force equation, the equation does not change, only the E and B and V, these depend on the reference frame, and these values should be properly used while calculating the force in a given frame. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.